Okay, so I have here before me an AP Calculus problem from the AB test from 2011. It's question 3. Not only do I want to demonstrate to you here how to go about doing this, but also that it can be done well within the time allowed, 15 minutes. So with that said, I should probably get started. Okay, the functions of f and g are given by f of x equals the square root of x. So that's this section here. I'll not draw that. And g of x equals 6 minus x. Let R be the region bounded by the x-axis, and the graphs of f and g as shown in the figure above. Okay, so we've got this region here, and it's bounded by the x-axis, so this is also our boundary down here. All right, find the area of R. So integrals should be like spinning around in your head right now. And what you should do is break this down into these two pieces right here, and just kind of start integrating with boundaries that make sense and functions that make sense. So the area of this entire region is going to be the area of this part right here, the area under that curve, plus the area under that curve. And so the area under this curve here, we're going to have cross sections that go like this, because we're going to be, this is how we're going to look at our function, and we're going to integrate across this way. So the area is going to be equal to the integral from 0 to our boundary 4 right here. That's an x boundary. Sure, x equals 4, x equals 0. And our function is square root of x. Dx, you're multiplying by a little differential with dx. Okay, so that adds up all the little areas of those little rectangles. Plus, for the second portion, you can either do it like this, the integral from x equals 4 to x equals 6 of 6 minus x dx, which is totally valid. Or you can also just see that this thing is a triangle with 2 here and a height 2 here. 2 times 2 is 4. Cut that in half. So this thing has an area of 2. And so that integral would simplify to 2. There's absolutely no reason to integrate for that, but just so you can see how you would if you were crazy and tried to integrate. We do, in fact, have to integrate this one, though. And so we can rewrite that as from x equals 0 to x equals 4 of x to the 1/2 dx. Then use our inverse power rule. So we're going to be going, it's going to be x to the 3/2 times 2/3, since we have to divide by the added 1, and then you flip it over because you're dividing by a fraction, so you can just multiply by that fraction. And we're evaluating that from x equals 0 to x equals 4. Plug in our boundaries here. We get that, well, if we plug in 0, let's see, we're going to have 2 chunks. It's going to be this minus 2/3, 0 to the 3/2. That's just 0. And this section over here, 2/3, 4 to the 3/2. 3/2, that's the power over the root, so it's the square root of 4 to the 3rd. 4 to the 3rd is 64. The square root of that is 8, so it's going to be 2/3 of 8, which is equal to 16/3. Plus, don't forget this, because people will, plus 2. And that is a perfectly acceptable answer for part A, find the area. They don't care if it's simplified. They'd probably prefer that it's like this. That way they can see exactly where you go wrong and possibly have a better chance of giving you points for other things, even if you don't get the whole thing right. Part B, the region R is the base of a solid. For each y, where y is between 0 and 2, so that's the y values from here to here, which is basically the range of our functions here. The cross-section of a solid taken perpendicular to the y-axis. Perpendicular to the y-axis. Okay, so that means the cross-sections are actually going like this. Sorry, it's getting kind of crowded up there. Rectangle whose base lies in R and whose height is 2y, right? But do not evaluate. Yay, an integral expression that gives the volume of the solid. So the volume of the solid is, now in this case, our cross sections are this way, perpendicular to the y-axis, which means that we should probably be trying to integrate in the y direction. So we're going to have y boundaries, and those y boundaries, oh sorry, this orange thing goes all the way to the other function because it's the region R, so there's like another one here and another one here. Y is going from 0 to 2, because this is our 0 and that's our 2, and so, you know, if you're adding up this way, you're adding them up in that direction, and you start at 0 and you stop at 2. What are we adding up? We're adding the volumes of the rectangles. Well, that's not really very specific, so what we're going to do now, well, what is the volume of one of those rectangles? Well, the volume of one of the rectangles is, and picture this like popping out of the page like that at you. The volume of one of those rectangles is its length this way times its height that way times its width, which is like a little sliver. Well, its width is just dy. Okay, so the width of the rectangle is dy, so we got that covered. Now we just need to find essentially the area of that rectangular plane here by multiplying the length. Its length is going to be the difference between here and here. So, you know, if I go somewhere on here, like here-ish, and I say, okay, what's the value of this function with respect to y? What's, you know, x of y? If I go here, you know, that takes me right there. And then I say, okay, that's that part. Now what about this part? You know, so that gives me this part. And then I can also find that part. So this part that I actually want here in a bright pink color is right there. It's the difference. It's the top function right here, top with respect, if you turn your head around and go that way, that one's on top, minus the bottom one over here. We need these functions in terms of y though, and so for this first one, y equals the square root of x, and so x equals y squared, just invert. And for this other one here, y equals 6 minus x, which also means that x equals y minus 6. So we have our top function, y minus 6, minus the bottom one, y squared. So y minus 6 minus y squared. And then we need to multiply that by its height. And it says that the height is 2y. So regardless of what's going on this business down here, the height of the function is 2y. So it's almost like you have some... Here, I'm going to try and draw this, and this should be funny. If you have like an XYZ plane or something, this is the x-axis, that's the y-axis, and this is the z-axis. It's almost like if you picture that you have your x-y-axis here, then we've got this thing coming, and then this other function, that line that was intersecting, and so this is our region R down here. Then it's like you have some sort of, the height is twice, the height grows in proportion to this y, so it's almost like you have this like plane thing that's coming up over and above this entire region, and it's like a plane that's cutting into your function region down there and giving you these weird cross-sectionally things that are getting higher as they go this way in the y direction. I don't know if that made sense. But anyway, so we need to multiply this width all by 2y. And so we have this kind of haphazardy looking thing, y minus 6 minus y squared all times 2y dy. Luckily, it says not to evaluate it and only to write it. And so that is how you would find the volume of that awkwardly shaped cross-sectional volume above the region R. Finally, there is a point P on the graph of f at which the line tangent to the graph of f is perpendicular to the graph of G. Find the coordinates of P. Okay, so we're trying to find, translating this into math talk, we're trying to find what the tangent line. Tangent line should be like derivative, but wait, we were integrating. It's okay, you can still take derivatives. At which the tangent line to the graph of x. So you're trying to find when f prime of x equals perpendicular to g of x. Obviously, that's not solvable yet, but perpendicular to g of x, well, this is just a line with a slope of -1. So g prime of x is -1, right? And if you need a little more justification on that, you could just say that, g prime of x equals, take the derivative of that, 6 minus x, the 6 goes away, and minus x, that's -1. So confirms the notion that this is a line with slope -1. So then, if you want something perpendicular, that means that the slope of this guy times the slope of the perpendicular, you'll see that written like that. That's kind of insignificant, but it's just a notation. And that's going to equal -1. So the product of the slopes is negative. No, that's not right. What am I talking about? The product of the reciprocal of the slopes is -1. In this case, it doesn't matter, because if you multiply the m perp over and divide by -1, you get m perpendicular equals 1, which kind of makes a lot of sense, because if you have some sort of line going in this way that has a slope of 1, it very clearly makes a right angle. So we're trying to find, now we can translate this, when f prime of x equals 1. And f prime of x is just given by 1/2 x to the -1/2. So we're trying to find when 1 over -1 over 2 root x equals 1. And that's going to happen when -1 equals 2 root x, when root x equals -1/2, and oh, there's no negative here, so that's on the exponent. This should be a positive. I was like, I don't think we have imaginary solutions. Plus, and so then x is going to equal the square root of 1/2, which is also root 2 over 2. And so that means, visually, that there's some point on, I need a new that means that there's some point on this graph, root 2 over 2 is like 0.707 something, so that's like right here. And if you look right here, it kind of looks like you have a slope of +1 there. And you can imagine it intercepting this guy and forming a perpendicular angle. And that is it for this AP problem. Hope you enjoyed.